Okay, a number of you are struggling with the actuator, getting that working in the forward dynamics simulation of the parking barrier. As general good practice for when you're developing a simulation, you don't want to put your whole model together with the barrier and the actuator and all the joints and then press play and hope for the best. It's good to test each bit as you put it in. So for example, if you've got what you think is a model of the actuator, do some simple tests on the actuator alone. For example, if the actuator, you've got the tube and the rod, start it out at some angle like, theta 2 equals 0, where theta 2 is the angle of the actuator. So if you start theta 2 out at 0, you're going to be applying a force to this actuator. So you could apply, say, a retraction force, a force that pulls in on the rod. And let's say you make that just a little bit less than the weight of the tube. Okay, so if the tube has mass m3, weight m3g, let's apply a retraction force that's a little bit less than m3g. Start the simulation from there. So at first, the rod is going to move in. And then as this thing falls under gravity, eventually the tube will get a bit more vertical. And now, the gravity force is going to overcome the retraction force. So at first the rod will go in, then the rod will slowly come out. So something like that, you'll see with that simple maneuver if your constraints are all working properly. Now, if you're going to define this actuator model, I think the easiest way is if you've gone back and reviewed the quick return mechanism, and if that makes sense, let's do a formulation that reuses as much of that as possible. So in the quick return mechanism, we had a link A to B2, and that was in a slot in link 3. So link 3 came up like this, and point B2 was supposed to be in the slot, and we defined a point B3 somewhere on the slotted link, and then we defined a vector delta R. It was xb2 minus xb3 in the fixed I direction, yb2 minus yb3 in the fixed j direction. So what we want to do here for the actuator is, I guess really what we want to do is we want to take this link and flip it around so that the rod part gets pushed away from link 2. Alright, so I think that it's a lot easier if you do all this in the first quadrant anyway. So for my actuator, I want to draw point A1 on the base, a couple of stiff springs, and now I'm going to go to the tube part of my actuator, which will have points A2, center of gravity G2, and point B2 up there. So once again, this represents the tube part of the actuator. Now if I go down and look at my quick return mechanism, I had link 3 and I had a delta R vector that was going up and to the right, so I'll do the same thing. Now I've got the rod part of my actuator, which is going to be like that, and there's a slight angular difference there which I'm going to penalize with a torsion spring. So for the rod, I'll call that B3 and I'll call that C3, and then I've got the center of gravity of the rod G3 right there. Okay, now just like in the quick return mechanism, I will define my delta R vector, and its I and j components are going to be x, b2, minus xb3. So that's the I component. yb2 minus yb3 is the j component. And I'm going to convert that into a frame that is aligned with, well, either the rod or the tube. Now, we're going to have a torsion spring in here. The difference between, I'll draw my theta up here further, the difference between theta 3 and theta 2 is going to be very small. So I think I'll just define a coordinate frame with an I2 and a J2 vector. I'll make it aligned with and perpendicular to link 2. If I had another one aligned with and perpendicular to link 3, it would basically be in the same orientation, so I'm not going to worry about that. Also, when I do my free body diagrams, I'm going to have, if the actuator is extending, an actuation force that's equal and opposite on the rod and on the tube. And I'm just going to align both of those with their respective links. So again, I'm working on the assumption afterwards that theta 2 and theta 3 are the same and that that actuation force acts in the same direction along both the rod and the tube. Okay, so now, just as in the quick return mechanism, I have to transform delta R into components along and perpendicular to these links. And the component along is going to have delta X magnitude, and then delta Y will be the magnitude of the component perpendicular. This is the one where the stiff spring is going to act. Okay, how do I do that transformation? I use a transformation matrix which you can derive. It's going to be cos theta 2 sine theta 2 minus sine theta 2 cos theta 2 times the delta R vectors components in fixed I and j. So the delta R2 vector I get, that'll be delta X, and that'll be delta Y. Now the spring force is going to be proportional to delta Y. To keep these two parts of the rod in in the same orientation, I'm going to need to put a torsion spring of some sort on here with a torsional stiffness KT. Alright, so when I do the free body diagram now, when I do the FBD of link 2, let's see, I'll draw A2, B2, A2, B2. I've got the center of gravity, I've got the gravity force, this links at theta 2. I'm going to have F12X and F12Y, which will be positive K times YA2 and XA2. Up here at B2, which was at the end of link 2, that's where the spring connected it with the rod. Right there, I am going to have a force that is perpendicular. I'll indicate here an exaggerated difference between theta 3 and theta 2. So this is going to be the force between links 2 and 3. Alright, so that's going to be perpendicular to theta 3. I'm going to show an actuation force, F, call it FAB, call it whatever you want. Call it F act for actuation. I'm going to make it positive when the rod pushes back on the tube and the tube pushes the rod forward. So when I do an FBD of link 3, I will draw link 3 at angle theta 3. I'll have B3, G3, and up here I'll have C3. That's going to join onto the barrier. But for now, if I'm just testing the actuator, I won't have any constraint forces up there. Alright, so I'm going to have F actuator directed along link 3, knowing that it's going to be pretty much the same angle as link 2 later. I'll have my equal and opposite F23 perpendicular. And now the sliding distance, the delta x, that was the component along the link of the distance from B3 to B2. So F23 acts from B2. So this is going to be delta x. So what's going to happen initially, for example, reminding ourselves that this is the tube. If I start this simulation out with the rod all the way into the back of the tube, here's B3 on the rod, here's B2 on the tube. Initially, I'm going to have a delta x, which is going to be negative something. Okay, because I'm actually going to have a delta x which is going to be positive. It's going to be the distance from B3 to B2. And as the actuator extends, delta x is going to shrink. Okay, so delta x will start out there. And then as the actuator extends, delta x is going to be, once again, from B3 to B2. So delta x dot will be negative when the actuator extends. So keep that in mind if you're putting in any viscous friction between the rod and the tube. Anyway, rest of the free body diagram here. For link 2, there is going to be a torsion spring. And if I define the torque of the torsion spring as torsion stiffness times, let's say theta 3 minus theta 2, that means if theta 3 is greater than theta 2, it's going to try to pull this rod down that way to line up. So if T32 is positive, I'm going to have a torque T32 that way on the link. Okay, and I'm going to have an equal and opposite torque T32 on link 3. So this is the free body diagram for both of these links, and with that you should be able to, like I said, do a first quadrant formulation using a lot of the stuff from the quick return mechanism, and then do some simple diagnostic maneuvers to make sure everything is working in the end. Other hints are, some people have started out trying to simulate for 1 second or 5 seconds. If your code is not running and then stopping on its own, simulate for 1/100th of a second. Also, for example, in your function that computes the derivatives for Newton's laws, you're going to do things like define stiff spring deflections. You're going to say XSA it's whatever, xg2 minus a2g2 cos theta 2. And then you're going to put a semicolon in so it doesn't print on the screen every time you call the function. If you delete that semicolon, then every time step it's going to spit out on the screen what XSA is. So if you think that one of your links is flying off into the cosmos because you've made a sign error in your stiffness, if you display the stretch of one of those springs every time step and it keeps getting bigger and bigger and bigger, well, then you know something's wrong. So you can unsemicolon whatever variables you want and keep track of how they're changing, and you can get a sense of what's blowing up and what isn't. For example, delta y, you might want to unsemicolon that and see if delta y is staying near 0, as it should. Okay, so hopefully some hints that will at least help you get the actuator done. After that, it should be relatively smooth sailing, and I'll post this document on the website.